of the day, which is on revealing disocclusions in temporal view synthesis through infilling vector predictions by Vijayalakshmi K. Vijayalakshmi received her B.Tech degree in Electronics and Communication Engineering from SSN College of Engineering in 2018 and is currently pursuing her M.Tech research degree at Department of IEEE-IISc. Her research interests lie in the intersection of computer vision, image and video processing, and deep learning. Welcome, Vijayalakshmi, and you may please start your presentation.
Thank you so much for the introduction, Devyani. Am I audible?
Yes, you are audible.
So I welcome all of you to my presentation, which is the topic of today's talk is going to be revealing disocclusions in temporal view synthesis for the application of frame rate upsampling. Jumping into the motivation behind this research, there's generally a lot of graphics that is rendered at high frame rates and high spatial resolution in virtual reality devices. Smartphones, and low compute devices, commonly for gaming applications, like we play games on mobile phones and so on. However, these are commonly low compute. They have very low compute capacity, and they generally cannot match the high frame rate that is needed to render at high frame rates. So what commonly happens is when they cannot match the high frame rate is that intermediate frames while rendering gets dropped, and what you perceive in the video that has been displayed is a jitter, which looks like the video gets stuck. So this is where we say that a frame predictor, which is an algorithm, can be very useful. This is generally low complex, and it can pitch in and generate frames periodically in conjunction with the graphics renderer. This reduces the load on the graphics renderer and also ensures that high frame rates can be mentioned for the end application. So at any point of time for such application, you'll have frames coming periodically from the graphics renderer as well as from the frame prediction algorithm. The frame prediction derives data information about the scene that's to be rendered, etc., from the graphics renderer for it to be able to predict the intermediate frames. So, like I said, this problem finds application in gaming for virtual reality, low compute devices, because we increasingly have such devices being employed for these applications. So, given this application, we have formulated this problem into Egomotion-Aware temporal view synthesis. Egomotion refers to the motion of camera in a rigid scene, typically as the camera's location and rotation in the world coordinates. So when such information is available for every scene, every frame in a scene, temporal view synthesis can use projective geometry to warp the current view to the next view to predict the next view. So in the context of frame rate upsampling, here we consider the application in our work. We consider the application where we upsample by 2, which means you have the frame, which means you have frame n minus 2, frame n plus 2, and so on coming from the graphics renderer. Whereas the intermediate frames, frame n minus 1, n plus 1, n plus 3, and so on, have to be predicted by our frame prediction algorithm. Further, the setup that we consider is also causal, which means we assume that to predict frame n plus 1, we only have information about frames that have already been rendered, which are frame n minus 1, n minus 2, and so on. So the problem setup is causal. I would like to stress on the fact that our problem definition is causal because you will see that later that in literature that this assumption is not very common. So from the figure, you can see that given a frame n that has come from the graphics renderer, we want to predict this frame n+1. What this usually involves is a key step called post warping, where you warp frame n, which has come from the renderer, using the camera pose and the depth of frame n and n+1. You do post warping and go to frame n+1. This is called the warp frame n+1. So you can see that once you do warping, you have almost recovered all of the all of the content that will be there in your frame that's to be predicted. But what is missing are these disocclusions. So disocclusions correspond to regions, they're opposite of an occlusion. So they correspond to regions that were not visible in frame n but become disoccluded in the view of frame n+1. So because this is unknown in frame n, when you warp and go from frame n to n+1, these regions appear as black holes. We commonly call them disocclusions or holes. So now the major challenge that remains is, or the problem that remains to be solved, is infilling for this disocclusion, which will be the focus of our algorithm. So I would just like to reiterate that the main challenge therefore in temporal view synthesis is infilling for these disocclusions. So the problem of infilling has been handled in literature in three broad channels, namely, four broad channels, namely novel view synthesis, image and video inpainting, depth image-based rendering, and video prediction. So in novel view synthesis, the common assumption, where we are different from novel view synthesis is that it's common to assume that you have multiple source views to predict the next frame. Whereas we here assume that we only have the previous frame. And then the other key difference is that novel view synthesis does not necessarily need ground truth depth. So some methods either estimate depth by themselves by terms of an estimation, or they use representations called multi-plane images, where the depth estimation is pretty noisy, it's not very accurate. So you can see that this may lead to errors when you do warping or synthesize the next view. And then the other key difference is temporal correlation. Like I told you, we focus on doing upsampling for videos, which means you always have temporal correlation that is coming from the usage of previous frames. Whereas novel view synthesis do not leverage this benefit. Moving on to image and video inpainting. So the word inpainting here is similar to what I call infilling disocclusions, because you have to complete a small portion of the frame or the image. It's image in image inpainting and video frames in video inpainting. One key difference is the causality, like I mentioned earlier. These video inpainting algorithms generally assume that the whole video is available. So when they have to predict intermediate frames, they know what content is going to come from the future frames. So they are at a greater advantage than us, where we don't know the future frames. So it's more challenging to predict what will come in the disocclusion. And image inpainting again does not exploit temporal correlation that is provided by videos. And then one other difference that is there commonly in video image or video inpainting is that the disocclusions on holes that they look to infill is generally irregular. Like you see here, they have been they've been masked using a white portion. So their algorithm, the aim of their algorithm would be to infill for these regions and get a completed and inpainted image. So the disocclusions in their case would be either arbitrary like patterns, or it could either be some fixed square region that they masked out, and then they say that we'll infill for these regions. Whereas you'll see that, like I showed in the previous slide, that in ours, the disocclusions generally have a pattern or correlation coming from the fact that it comes from the motion of camera. So it sort of follows a fixed trajectory. So you know that disocclusions will occur only at certain places and only in certain shapes. So it's rather not as arbitrary as it is defined for image or video inpainting. So then coming to depth image based rendering. So their approach is to say that because these disocclusions commonly, they have to the infilling has to come from the nearest background. These methods say that I'll first separate the foreground and the background, and then I'll complete the background, and then I'll superimpose the foreground and the background to get the infilling. But this is a rather inconvenient process to do, and the use of deep learning has also not been explored much. So finally, coming to video prediction, this is probably the closest to our problem definition, which is temporal view synthesis, where we say that we want to predict a future frame. But we are at the key difference is that these video prediction algorithms generally say that I'll take past frames or past and future frames, and they tend to predict. I mean the frame to be predicted from the scratch. They synthesize all the pixel values from the scratch. You can see that this is also a great advantage because it can lead to a lot of distortion in the frame. Whereas like I mentioned earlier, we leverage something called projective geometry because we assume we have camera pose, the trajectory information. So when you do the pose warping itself, almost all of the frame to be synthesized, we get it through the warping. But video prediction has to go through this unnecessary step of synthesizing all the RGB frames from scratch. Whereas we make effective use of camera motion and scene geometry effectively. So given the limitations of the following approaches, we at this point propose the use of infilling vectors to do the disocclusion infilling. So this is based on the assumption that the disocclusion which has been marked black, I mean they have been masked here. The fundamental assumption is that to infill for these disocclusions, you needn't look for information anywhere in the frame. It is present in its immediate neighborhood itself. So you can see that when a foreground object moves and it disoccludes a portion of the background, like I said, it's a portion of the background itself. So you can look for information in the nearest background, and you can infill using that information itself. So to read off from the nearest neighbor, I mean from the nearest background, we propose to use what are called infilling vectors. They're in some sense similar to the flow vectors that people might already be familiar with who are working in this domain. So they are basically pointers that point from one location to another location. So here also the infilling vectors points from a location in the background to a location in the disoccluded region. It says that put this value from the background into this disoccluded portion in my warp frame. So one more thing that needs to be noted here is that we apply these infilling vectors on the warp frame n+1 itself. So when it comes to doing the sampling from background, we don't again use the past frames. We do it from the warp frame itself. The warp frame itself has sufficient information to infill for the disocclusions. So some key advantages with using infilling vectors is that when you synthesize, for example, which is generally common, if you synthesize pixel values for these disocclusions based on the neighboring information, they are more prone to errors. So the errors come in the form of blur. I mean, they look very smooth. If there are any textures, they are not recovered properly, or they come in the form of color gradients because they tend to sort of average the foreground color and the background color, which might not be necessary. We clearly know that it's a background, so we don't want any kind of foreground leading into the disocclusion. So further, if we use infilling vectors, they give us the advantage that because they are vectors, they have direction information. So we can impose constraints on the infilling vectors and say that you have to only infill from the background. Further, like I said, because we use pass frames and camera pose of pass frames, we can impose some temporal similarity or temporal correlation that enforces better prediction of infilling vectors. So like I said, given this frame n, the current frame n, the key step is warping the frame from the view of n to the view of n+1. So to go from frame n to n+1, what we need is the frame n, and then we need the depth map for frame n. The depth map refers to the depth map is basically it's a map where for each point it indicates the depth of the object at that point or the pixel at that point in the scene. So given the frame n, the depth map n, and then the transformation matrix, which is what I've been calling the pose information all along, it describes the transformation that will take you from the view of frame n to n+1. So it basically describes the change when you're looking at frame n to what you're looking at in frame n+1. When you leverage all these, information fn, dn, and then the transformation matrix, you can put them into a nice geometrical equation that takes you from the view of P, from a pixel P of n present in frame n to the view of frame n plus 1. So you do this for every point in the on the grid of frame n, and then you reach frame n plus 1. The points that don't have mappings are what are the disocclusions. They will automatically be indicated by a black portion, which we can infill using our algorithm. So there are two key aspects of our infilling vector prediction algorithm. So as I mentioned earlier, camera motion in a video tends to be correlated across time. So tapping this information is easy with infilling vectors because they exhibit similarity in their direction between successive frames. You know that between one frame and the next frame, there's not going to be a huge discontinuity in the camera motion. So this similarity or uniformity in the direction we can use to our advantage. So to predict frame n plus 1, so now to predict frame n plus 1, I said that we have the past frames. So which means we have frame n, we have frame n minus 2. So the first step in our algorithm towards infilling vector prediction is we take this frame n minus 2 and warp it to the view of frame n. So you now have a warp frame n, but you also have the ground truth frame n, which means you can do a crude estimation of the infilling vectors corresponding to frame n. The idea behind doing this is that if you know how infilling was done in the past, you can leverage the same to tell the network how to do it for the current frame n to n plus 1. So when you have this warp frame n minus 2 and n, so for every pixel in the disoccluded region here, we can do a crude matching algorithm, I mean a pixel-wise MSE matching, and find out what is the best pixel that can be infilled here from its immediate background. So we search in all four directions for a given pixel x comma y. We search in left, right, top, bottom. But the closest match, will come only from some portion here, because that correlates to that will match best with the true pixel of present in frame n. So like this, we do estimation for all disoccluded pixel in the warp frame n, that is warp from n minus 2, and then you get vectors. The vectors, like I said, correspond to the x direction, the height. The x direction width and the y direction height. So like this, you get a two-channel map that indicates the estimated infilling vectors. But this is corresponding to the warping between frame n minus 2 and n. So at this point, what we do, we warp frame n to n plus 1, which is a common step, and then we also warp these estimated infilling vectors to the view of frame n plus 1. The idea behind warping these infilling vectors is to align the infilling vectors to the view of frame n plus 1 to bring all of them into the same alignment. So here the interesting thing is that you can again see some correlation. So as soon as you warp the infilling vectors for frame n to the view of n plus 1, you can see that near the disocclusion present in frame n plus 1, you have the infilling vectors, the previous infilling vectors that have been warped, and they will correspond to this portion. So given this prior, we say that if using these infilling vectors, we know what infilling vectors should come here, then that is all we need to infill frame n plus 1. So to do this prediction, I mean to get the pixel values for this region based on this region, we leverage a deep neural network. So this is the temporal guidance portion. We also have the depth guidance, which comes from the fact that, like I said, we only want the infilling to be done from the background. So in what way can you tell the network that you should only infill from the background? This you can do by feeding the depth map. Like I said, as you warp the frame n to n plus 1, you can also map the depth map. You can also warp the depth map of frame n to n plus 1. So once you do this, again, you can see that the depth map will also correlate in a similar way, and say that next to the disocclusion, there is the background, which is the valid portion, and then the foreground, which is the invalid portion. For a foreground object, the depth is small, and for a background object, the depth is large. So the network will be able to differentiate to decide. I mean, it provides a useful cue and says which is the background and which is the foreground. This is especially useful when for low frame rates. So when you have low frame rates, it means that you have a larger change in viewpoint from frame n to n plus 1. So the correlation between the camera motion automatically drops a little. So which means at this point, our estimated infilling vectors may not be very accurate, which means so at this point the depth guidance can pitch in to I mean can pitch in to and guide the network to say which is a valid background. And then the other case where it's useful is when you have multiple backgrounds. Like if you have a cluttered background where you have a wall and then in front of the wall you have a pot probably. You want the network to decide whether the infilling vector, the disocclusion corresponds to a pot or the wall. So in the relative background, the wall is in a farther background compared to the pot, for example. So this the depth map can again automatically capture, because compared to our immediate foreground, the pot will be further and then the wall will be even further. So the network knows that okay, this is a relative background that's more relevant for infilling. So given this setup, we have constructed an infilling vector prediction network, which is a unit. So it's a simple unit that consists of a couple of upsampling and downsampling layers. This network takes as input the warped infilling vectors, which I just described. So like I said, it has infilling vectors coming from the prior in the neighborhood of the disocclusion. And then we tell the network, hey, give me the values for give me the infilling vector values for the disoccluded region also. And because I said that we also want to use depth cues, we take the warp depth that has been warped to the viewer frame n+1, and then we process it by a couple of convolution layers to the range 0 to 1, because the depth value, I mean, we just want to normalize it so that the network can make better use of the data. So we pass a concatenation of these two data to the network, and at the output we get, in some sense, infilling vectors. So at the output of the network, even this portion will be completed, and you'll get finite values of vectors. So now this infilling vector we take and we do sampling on top of frame n+1 itself, and then you get the infill frame. So what will happen? You pass it to a spatial transformer, which is nothing but a sampler kind of. Uh, so what it does is it goes to a known location in the background of frame n+1, takes that pixel value and puts it in the disocclusion of frame n+1. So this is formulated as the following equation defined here, where you take the warp frame n+1, and then at each location you add the infilling vectors corresponding to the x and y directions, and then you get the destination location where the pixel value at this position was, and put it at x comma y. So this network we have trained using a combination of three losses: MSE, SIM, and smoothness. MSE and SIM contribute to the reconstruction loss. I mean, they correlate with what we perceive in the infill frame. And then smoothness is applied on the infilling vectors, because we want the vectors to be smooth with respect to each other. We don't want one infilling vector pointing in one direction and the other infilling vector pointing in another direction. We want them all to be correlated and only pointing towards the background. And the smoothness loss will be useful in giving this, in enforcing this. And the MSE and SIM loss we estimate in the unknown region. I'm sorry, by unknown region I mean the disocclusion. We'll be able to easily obtain a mask that indicates which is the disoccluded region, which is the known region, and we get it during the post warping process itself. So we have conducted experiments with these models. We've conducted experiments on two databases, which is CNET RGBD, and then our database, which has been constructed using Blender. So CNET RGBD is a large-scale database. However, the spatial resolution is low, and the frame rate is also pretty low. And then we found that this is generally the case for many databases that's currently found in literature. Even if we find databases with high spatial resolution or temporal resolution, they do not provide camera pose or depth. But it's key to the formulation of our problem that we need camera pose as well as depth as well as high spatial and temporal resolution, which is why we went on to generate a database. I mean, make a database on Blender. So we picked 3D models of indoor and outdoor scenes and fixed cameras and trajectories, and rendered these videos at full HD resolution and at 30 FPS. Because we were able to render the database, we made sure that we captured camera pose as well as depth. So given these two databases, I've chosen, I've chosen to present results based on three algorithms. Like I told you earlier, we have relevance to problems. We have relevance coming from problems like novel view synthesis and image in painting. So I've chosen one algorithm from each section. StereoMag and Synsin are two view synthesis algorithms. VINet is a video in painting algorithm, and EdgeConnect is a image in painting algorithm. So you can see that of all the methods, StereoMag is giving very poor performance. So you can see that in the disocclusion, you can see that there's a lot of color gradation and blur, which I mentioned earlier. You can see that in the disocclusion, instead of the background being infilled, almost all times you have the foreground coming in, or you have a lot of blur. This is because StereoMag does not take ground truth depth as input. They resort to using a multi-plane depth representation of the scene and so on, but it's still not very accurate. So moving on to Synsin. Synsin does comparatively better, but we still see a lot of problems with respect to irrelevant colors being coming in the disoccluded region. Because again, this is a method that synthesizes the RGB values from the scratch based on the RGB values in the neighborhood. This is again problematic because, like I said, the foreground pixel values can bleed into the disocclusion, which is not necessary. So in video in painting, yeah, this is a video in painting algorithm. They assume the knowledge of future frames. So they assume they have to predict n plus 1. Their original formulation assumes they have n minus 1 and so on, as well as frame n plus 2, n plus 3, the future frames also. So you just have to predict the in-between frame. But yeah, because our problem definition is causal, we had to test only by providing the past frames to the network, and we can see that it has taken a blow on the performance. The network was probably expecting to see future frames to see what should be infilled in the disocclusions. But since it's not available in the past frames, we can see that it's commonly infilling from the foreground. Here also you can see that the chair has been extended, and here the corner of the box has been extended. So EdgeConnect is the closest competitor, but it still suffers from one major disadvantage in that you can see that there is blur. The prediction is not sharp. Even though the colors are pretty close, you see that there is still a color shift. There's still a color shift. But IVP is able to overcome all of these limitations, and you can see that in the disoccluded region, the infilling is extremely close to the true frame. In this example where there is a texture and pattern, you can see that our infilling vectors are able to predict where to relevantly infill the disocclusions from. This is the case for all the examples. You can see that the box square here has also been very precisely maintained. And then coming to the last example also, it doesn't matter whether the disocclusion is vertical or horizontal. It's been inclined at approximately 45 degrees, but it doesn't matter because they are infilling vectors. They are able to know the orientation of the background, and it has sampled perfectly from the background. The pattern of the woodwork has also been recovered very well. So irrespective of the nature of the disocclusion, in that whether the disocclusion is plain or the background is textured, has patterns, IVP is able to recover them well. So I presented some qualitative analysis now. Quantitatively also, our method is showing very good numbers in terms of MSE and SIM. MSE is mean squared error. So infilling vector has very low MSE, and then SIM is a perceptual quality measure where the higher the value, the closer to 1 it is, the better. And we see that in terms of SIM also, infilling vector predictor has higher values. And this is true of both databases. We can see this pattern on both databases. So DSIM and DMSE are the corresponding metrics measured only in the disoccluded region. Sometimes it's relevant to see how they do only the disoccluded region because, yeah, that is the portion that's synthesized new. So we also measure DSIM and DMSE. Even there, we show very good improvement over the current methods. So, like I said, a network takes input as to guidance in the form of temporal guidance and depth guidance. So you can see that for the example in the first column, here we did not provide the temporal guidance. So we just passed the walk frame to the network and asked it to predict infilling vectors for that frame. So you can see that in the disoccluded region, there are a lot of foreground infilling that has been done. This is because, so this is because, like I said, the temporal guidance also gives cue on the direction of the background. So when that was absent, it was easy for the network to make mistakes. And so it resulted in foreground infilling coming in the disoccluded region. In the second column, we show an example where we did not provide the depth mask. So like I said, the depth mask can be useful when when you have multiple objects, or when you have or when the camera motion is not correlated, when there's a slight change in the camera direction. So this was the case with that example. There was a slight change in the camera direction from n minus 2, n and n plus 1. So at which point again the temporal guidance uh, could be wrong. I mean, could be wrongly guiding the network. So when we did not provide the depth mask, I mean, it showed that the infilling was being done from the foreground. Whereas when we provided the depth mask, the network, in spite of the temporal guidance maybe pointing to the background, I mean to the foreground, the depth mask was able to say that no, the infilling vector should come from the background instead. And then another a small portion of our algorithm is this iteration. So what we do, for a single pass of the network, you get the infilling vectors. So what we do is we check if there are any invalid infilling vectors in the form of those pointing to the foreground. We remove them and then we pass them in the next iteration to the network again and get infilling vectors. We do this iteration 3 times, and we've seen that at the end of 3 iterations, the infilling vectors are pretty clean. And you can see the effect of using no iteration. By no iteration, I mean there's only a single pass of the network. So any invalid pixels are not removed. Although the number of invalid infilling vectors are small, they are just small. It means a network is almost successful. But with iteration, we were able to remove even those small inconsistencies in the infilling vectors that were predicted. So finally, we just compare with intensity infilling, which means so what we did was we took the walk frame and just passed it to the unit and asked it to give us the infill frame. So this is again extremely problematic because when you have upsampling, downsampling layers or any convolutional network, it's quite possible that I mean you cannot avoid the foreground from bleeding into the disoccluded region. Whereas if you use the infilling vector prediction algorithm, you can see that this is, so the frame that you're looking at right now is our prediction, and you can see that it's extremely clean without any distortion or foreground pixels. So, another benefit for our method comes from using the smoothness loss that I just mentioned. We see that this is extremely useful in recovering textures because, yeah, like I said, disocclusions can be of any nature, smooth, textured, patterned, and so on. So at which point smoothness is very important. So when you have the smoothness loss, it allows the infilling vectors to actually sample from blocks of regions, right? So like here you can see that the true frame actually has extremely small squares, which is a pattern. So compared to the image inpainting algorithm, which has completely blurred out the texture, IVP is doing a much better job of recovering the square patterns. The same is the case with the second example where the background here has again very intricate, has an intricate pattern. The inpainting algorithm has smoothed it out obviously, whereas IVP is so much more close to the true frame. That is because the smoothness loss was able to enforce the infilling vectors to sample such that the patterns were being maintained. So finally, let's look at predictions on a few videos because I've been saying that we use videos, and I've only been showing images. So to get video results, what we did was, so yeah, like I just discovered, we took frames at 15 FPS, and then we predicted the intermediate frames. We predicted the intermediate frames and inserted them to get a 30 FPS video. Note that we did not use any future frame. We've only used the past frames. Okay, the video is not playing for some reason. Okay, so okay, for some reason it's not playing. I'm sorry, but I think you can see the video where we used Synsin to predict the intermediate frames. You can see that there's a lot of flickering because, like I said, there's almost always foreground infilling. So in the disocclusion, you have color shift when you alternate between the predicted frame and the true frame. You you sort of see an alteration. You sort of see alternate frames that have perfect infilling, whereas I mean, you have alternate frames that have perfect infilling and imperfect infilling. So this you can perceive as flicker. This is extremely unpleasant when you have virtual reality applications or gaming applications. So the next comparison we do it with Edge Connect, which is the image inpainting algorithm. So here you can see that the disocclusions commonly come where the regions where you should focus are where we have constructed the rectangles where the disocclusions occur. You can see again flicker near the disoccluded regions. Our videos is almost clean, and I'm sure it will be it will be the closest to a 30 FPS originally rendered video. Whereas Edge Connect near the disocclusions, it's often averaging from the foreground and background and giving rise to these flicker. We also show it with the depth image based rendering algorithm. This algorithm also suffers from the same artifact, and you can note them at the edges of objects. Where there's a difference between foreground and background, the flicker is very apparent. Whereas ours is extremely clean, the color is consistent also. So this is what we have been working on as part of my MTech research. So in terms of future work, what we aim to do is, I know we have said that we have ground truth depth available, but we have realized that for real videos, for gaming applications, it's generally synthetic, so it's always possible to obtain ground truth depth. But for real-time videos, depth is often not available. So you have to get an estimate of the depth map for the scene, and we've observed that it's not always accurate and presents some challenge in terms of post warping and infilling. So the first line of future work would be to assume that ground truth depth is not available. So we have to look for options like where we modify the algorithm to handle depth estimation, and also employ this estimated depth to better supervise and guide the infilling vector prediction. The other future line of work comes from using the flow. By flow, I mean the motion of pixels from frame n plus 1 to n. So we say that because we have the camera pose information, this flow can be easily estimated. So we want to see how this information can be useful either to predict infilling vectors itself or in general to predict the disocclusions in frame n plus 1. So we have submitted this work to the Winter Conference in Applications of Computer Vision, and we might get a result soon. So with this, I'm open to questions.
Please feel free to ask questions. All right, I think there are no questions. Thank you, Vijayalakshmi, for the talk.
Thank you so much. It's been my pleasure.
Yeah. So, and also, please accept this memento from IEEE-IISc ComSoc and SPS chapters. We wish you all the best for your future endeavors.